What? Maybe we should go to Hangfeng.
All right. I just want to ask a question following on your discussion on field. So how do you define a boundary between rigorous and empirical, or how do you understand the term first principle?
It's a good question. You know, down in the Ruliad, we might actually have the true first principles in some sense. But most of the time, I mean, let's think about that. I mean, I'm thinking about things I've seen in the second law of thermodynamics, where people were trying to prove the second law from the laws of mechanics. And for them, mechanics was first principles. You know, in other words, mechanics was solid, and then everything above mechanics was something you got to prove. I was a little bit surprised, actually, in some of the literature, how solidly they took mechanics, so to speak. But I mean, it's an interesting question, I suppose. What's an example of a field? I mean, give me an example of a field, and I can perhaps be more useful on that.
So I want to follow up. So in last talk, you mentioned we haven't seen a true scale bridging from molecular scale to the continuum scale, like the partial differential equation. We haven't seen actual rigorous proof on that. And I truly believe that, because I think, say, in the molecular scale, a lot of interatomic potential are fitted based on assumptions by applied mathematicians. And in the continuum scale, a lot of equations describing like the fracture of solid are also just data fitting the experiment. But then it go to the second law of thermodynamics, or quantum physics, are more rigorous or first principle based, right? So that's like, this is my,
I think you're seeing computational irreducibility there. You know, there is a distance between the underlying laws and the overall behavior, and there is an irreducible distance between those. And there are cases where, you know, where you will not be able to have a useful, quotes, first principles derivation, because yes, you can say what the underlying laws are, but there's a depth of computational irreducibility that you have to go through to actually see what the consequences are. Now, we are lucky in some cases, like the transition to the continuum, where it seems to be the case that we've picked up a slice of reducibility that you know, that we can latch onto, so to speak, that that doesn't require us to go through all these layers of irreducibility. So I think that's probably, you know, it's funny because people say, let's prove Fermat's last theorem, okay? And we're going to prove it from first, you know, we're going to prove it. So, you know, I remember I ran into Andrew Wiles shortly after he did that proof. And I asked him, so what axioms did you use to do this proof? He said, I have no idea, which is interesting. Because he not only did he not know, but he didn't care either. I mean, we had a whole conversation about it. He said, look, I'm pretty sure it uses a bunch of set theory. I'm pretty sure it goes beyond pure arithmetic. Does it need to go beyond pure arithmetic? Probably not, but in practice, it's going to set theory. But in other words, you might have thought that something like that, where you're saying, I'm proving this big theorem, it really depends on what you know, what were the foundations. But actually, that's not, you know, strangely, that wasn't the main point. And I think now, from these efforts we've made in metamathematics, it becomes a little clearer why it doesn't matter, for the same reason it doesn't matter what the underlying molecular structure of matter is to the continuum behavior. Similarly, in mathematics, it doesn't matter so much what those underlying axioms are to the sort of larger scale mathematics that you get from at the level of Fermat's last theorem and so on. So anyway, interesting question. All right, let's see, we go on here.